Okay, hi everyone. This is Pivot Physics. My name is BAARATH. So we're going to go through the either or question in the November 2025 paper 3. Okay? Okay, let's look at question number 8. So they are first asking you to define magnetic flux. So you know this equation. Flux is given as BA times cosine theta, where angle theta is the angle between the normal and the magnetic field. So by definition, we say that it's the product of the flux density, which is B, and the area of the surface, which is A. Okay, so this is how you define. So in part B, we have a square coil of 300 turns. So I'm going to call that N. I'm going to move it through a region of uniform magnetic field. The value is 4.2 millitesla. So this is the square coil, okay, of size 6 cm. It is 2 cm away from the region of magnetic field. They said that the magnetic field is perpendicular to the plane, and the speed of this coil is given as 4 cm per second. Now, the trick is to always work in terms of SI units. So that will give you 0.04 meters per second. Always we work in SI units. Okay. The length of the field is given as 22 cm. And they're asking you to show that the EMF induced is 3 millivolts. So the equation that I'm going to use is BLV, because a square coil is made up of straight conductors. So as your coil moves through the field like that, this is your square coil is going to move through the field. So as it moves through the field, the part where EMF is induced is this green region. So that's a straight conductor. So the equation is BLV. That's the equation that we're going to use. Right? EMF induced in a straight conductor, BLV. And for you to use these equations, these three quantities must be all perpendicular to one another. So B field is perpendicular. It could be into the page or out of the page, doesn't matter. Your length is perpendicular to the speed, and that is again perpendicular to the magnetic field. So you can simply use this equation. But this is only for one rod, one conductor. Now, don't forget, you have 300 rods, 300 turns. So the equation I'm going to use is BLV multiplied by N. Convert everything into SI units, you will get your answer. Now, here they're asking you to sketch the induced EMF from time equals to 0 all the way to time equals to 8. Now, when your square coil haven't entered the field, that means from this point all the way to that point, that will be 0 EMF, as shown by this value. So you already know the speed. The distance is 2 cm. That means the time for you to travel this amount is half a second, which you can see here, half a second. This is 1, that is half. And once your coil is now entering the field, that means all the way like that, that will induce an EMF, which is given by whatever you have calculated, which is 3 millivolts. So that is shown here. Now, when the coil is moving within the field, so from here all the way back here, within the field, EMF must be 0. So you know that your coil side, which is this, is 6 cm. So to travel from this point all the way there is going to be 22 minus 6 cm. So that is the distance. And given the time, and given the speed, you can calculate the time. That means it's going to travel another additional 4 seconds. That's right. So when the coil is moving within the field, the EMF must be zero because there's no change in flux or flux linkage. So from here all the way right there, EMF must be zero. But when it's exiting, now the affected portion will be this rod. EMF is of the same value, which is the 3 millivolts, but it must be now in the opposite direction, as shown by this value, all right, which is -3. So once it exits, you will have 0 as per what you got initially, all right? So that explains this particular graph. Now, in part C, they say that I'm going to replace that square coil with a circular coil. The diameter is the same, which is what I've drawn here. So that means now the circular coil is going to be moved. So same thing, for the same amount of time, which is ½ second, you will have an EMF of 0. But now when I enter, can you see that as the coil is entering, more and more magnetic field passes through the coil. Can you see that? So as I move even further, more and more field lines passes through. So your EMF must increase. And once it reaches the halfway mark, now can you see that this amount is becoming smaller and smaller? This white region here, can you see that? Is becoming smaller and smaller. So that means if I were to draw the graph for this circular coil, which is what they said, because the square coil is replaced by this circular coil, and you're supposed to sketch the induced EMF. So that means your graph should have an initial increase and then a drop, right? According to Faraday's law. So same thing, while moving within the field, your EMF is 0. When it exits, it must be in the opposite direction. The concept is the same. So just take note, because the values are not required, you must show an increase followed by a decrease. So why is an increase? Is because as your circular coil is entering, can you see that your area is becoming bigger and bigger? And then when the coil passes the halfway mark, this white region now becomes smaller and smaller. All right, so that explains the shape of that graph. Okay, so now they're asking you, if I now take the square coil, which is part B is the square coil, and I connect the ends together. So that means this square coil here, I'm going to connect the ends. So if I connect the ends, it becomes a closed circuit. That means current can now flow. So when this closed circuit is going to enter the field, you will first have an induced EMF because there's a change in flux, according to Faraday's law. But now, because it's a closed circuit, you will have an induced current, according to Lenz's law. And you know, induced current always flow to oppose the change. So it creates its own magnetic field, magnetic force. That means from Fleming's left-hand rule, now the force must be acting in the opposite direction to the motion. So I'll give you an example. Okay, let's say to make things simple. Okay, so this is that square coil that is entering. So let's say it's going to enter that field. Assuming, to make things simple, let's say the B field is into the page. So now using your Fleming's left-hand rule, FBI, B field is into the page. One second. So let's say your B field is into the page. Now I'm going to show you where exactly is your force, because your motion is to the right. So by Fleming's left-hand rule, FBI, B field into the page. Your middle finger should point in the upward direction. Index finger goes into the page, and your magnetic force must be to the left-hand side. That is your magnetic force. This is what we call as the opposing force. All right? So again, if you use Fleming's right-hand rule, so right-hand rule is to ascertain the higher potential. So if I use right-hand rule, again, MBI, M is for motion, motion is to the right, B field is into the page. So the middle finger points to the higher potential. This must be the higher potential, that is the lower potential. So current flows from the higher all the way to the lower potential, external circuit. Inside it flows from minus to plus. So again, if you're going to use your Fleming's left-hand rule, FBI, current flows up, B field into the page, your force is to the left. So if you want to move at a constant speed, your applied force must be equivalent to this magnetic force. And this magnetic force is calculated by that BIL for one rod times N if it's multiple rods, right? Right? So to ensure, like I said, that the coil moves at a constant speed, this magnetic force must equals this applied force, right? So the magnetic force can be calculated by BIL times N, which is the number of rods. So that's the concept here as to why you need work done to move it at a constant speed, right? So according to Newton's first law, for you to move at a constant speed, you need a rightward applied force, as I showed you just now, which is equal and opposite to the magnitude of that magnetic force, FB. Okay? So then you know that work done is force times distance. Yeah? So that's why you need work done. So that's the concept here. Okay. The next part, a magnetic field is produced using a solenoid. You have a wire, that's the length, this is the resistance. They wound it round a hollow cardboard. The cylinder diameter is 3 cm, right, as I've drawn here. So that's the wire, the resistance is given, this is the length. We also said that the EMF is 1.2 and the magnetic field produced by this solenoid is 4.2 millitesla. So you want to find the length. Now, B field of a solenoid, you know this equation, mu naught I, which is current, times number of turns over length. In some schools, they will teach you as mu naught I times small n, or meter, which means the same thing, which is turns per unit length. Here I have expanded it out, all right, number per unit length. So I want to find the length of the solenoid. I make that the subject. To find the current, we use Ohm's law, which is EMF over resistance. The EMF you know, the resistance you know. To find the number of turns, what you do is you take the length of the wire divided by the circumference, which is pi d. So all you need is to simply substitute these numbers and then you will get 0.169, right? So now the next question, why a solenoid is unsuitable for producing the magnetic field? Because firstly, you must understand, if this is a solenoid, I know you have uniform magnetic field at the center, you know that, but at the side, usually the field is smaller than at the center. Usually it's about 2 times smaller. So that means the B field at the side is approximately half of the B field at the center. That's right. Because that's a property of a solenoid. So it's incapable of giving you a uniform magnetic field. Okay? And another reason why this particular solenoid cannot be used is because they said that the diameter is going to be 3 cm. But the square coil, the side, is given as 6 cm. So obviously the square coil cannot enter this solenoid, right? So it's impossible to even use it in the first place. So that will be the 2 reasons, okay? Lastly, I want to find the diameter of the wire given its resistivity. You know this equation, rho L over A. Area is pi r square. R is radius, which is diameter over 2. So all you need is to substitute these numbers. You will get the diameter. All right? So that is for question 8. Now let's go to question 9. It's on gravitational and electric field. So they're asking what's the field of force? So by definition, we say it's a region of space where if you place an object, that object will experience a force because of its property and how that property interacts with the field. But the keyword is you do not need any contact. There's no need for any physical contact. Okay? Part 2 is the two similarities and two differences between E field and G field. Now, so you know this equation, electric field is Q over 4 pi E naught R square. You know that G field is Gm over R square. Both of them, they follow the inverse square law. All right, 1 over R square. So that's the similarity. And the second similarity is, both of them, they do not require any contact for you to experience a force. Like, for example, the Earth and the Moon, there's no contact, but there is a gravitational force. You have two charges that are spaced apart. There's still a force. There do not need to be any form of contact. All right, so that will be the two similarities. But you must know that electric force can either be attractive or repulsive, but gravitational force are always attractive. So if you have a plus and minus charge, they will attract. Plus and plus, they will repel. That is for electric force. But gravitational forces are always attractive. All right, so that's the difference. And of course, electric field acts only on charges. Gravitational fields acts only on masses. Okay, next one. We have a planet here with one moon. They've given you the masses of the moon. They said that the spheres are of uniform density and they are both spheres. You're supposed to show the radius of the moon. They've also given you the value of the G field strength, which is 2.71. Now, you need to use this equation, Gm over R square. I want to find the radius. So you substitute the values, you will get your answer. Now, important. G is not 9.81. Remember, this is the moon. So that's a common mistake made by many students as well, right? Noting that G is 9.81. That's wrong. Next. Why the G is no longer 2.71 on the surface? Now, this is not Earth. So you cannot say that, oh, the Earth or the planet bulges at the center. That's incorrect. That's number one. The second thing is you cannot say that, oh, the moon is not a perfect sphere because they already said it's a sphere. So you cannot assume that. Number three, you cannot say that it is of non-uniform density because they already mentioned that it is of uniform density. All right? So the reason why the G is no longer 2.71 and why it varies with position is because you know that the moon and the planet is pretty close by. And the planet will give you its own G field on different parts of the moon. And you know that G field is a vector. So the resultant is the vector sum of the moon's G field and the planet's G field. So that's why your value will never be accurately 2.71. Right? Because you need to vectorially add the planet's G field as well. So closer to the planet, which is this part, this red part, that part will have a larger G field strength because it's closer to the planet as compared to this green part, which is further away from that planet. All right? Now, we have a null point where your G field strength is 0. You want to find the smallest distance from the surface of the moon. Okay. So, let's say that's your null point. You must remember, null point is always closer to the smaller mass. Right? So, in this case, the null must be closer to the moon. So, for you to have null point, the G field because of the planet and the G field because of the moon, you know that G points radially inwards towards the mass. They must be equal and opposite. So Gp equals to Gm. So I'm going to call this distance d. I'm going to call this distance the 2.67 times 10⁸ minus d. And then we're going to simply equate them. So Gp equals to Gm. So you already know RP is the distance from the planet's center to the null. RM is the distance from the moon's center to the null. So all you need to do is to simplify. Now, if you see a quadratic equation, all you need to do is to square root. Never solve it quadratically, right? And of course, we neglect the minus sign if there is. So once you solve, you will get the distance to be 2.49 times 10 to the power 7. But you want to find the distance from the surface. Because what we calculated is this distance, d. So you take this d minus the radius of the moon, which is already given here, 1.54. And you will get 2.34 times 10 to the power 7 meters. Okay? Next question. Why the potential at the null is never zero? Because potential is a scalar. The individual potentials add up to give you a non-zero negative value. Because your individual potentials are already negative. Because of the moon and the planet, you algebraically add them up. Because potential is a scalar quantity. So that's why it will never be zero. We call it non-zero. Alright? So how do I calculate this potential? So you individually add them up. You know potential is minus gm over r. All you need to do is to substitute. So rp is the distance from the planet's center all the way to that null, which we have drawn in the diagram. Rm is the distance from the moon's center all the way to that null, which is given by whatever that you have calculated, which is the d that we have. Once you substitute, that's your answer. Now, finally, we have two charges, and they said that now the electric potential along the line will be zero. But why you will never have an electric field strength to be zero along this line? Why? Because you must remember, if your potential is going to be zero, that implies that your charges must be of opposite signs. One is plus, one is minus, opposite signs. And you know that potential is a scalar. That's why plus and minus, they will cancel out to give you zero for potential. But if it's a plus charge, so for example, if you have a plus charge, your field lines will point radially away. Right? Something like that. Maybe let me make a better drawing. So let's say you have a plus charge here. You have a minus charge here. So the plus charge will have field lines pointing radially away. Minus charge will have field lines pointing radially inwards. So along this line, this is the line that they're talking about. Can you see that your electric field lines point in the same direction? Can you see that? The individual electric fields point in the same direction. E field is a vector. So if you want to find the net E field, that is going to give you the vector sum, which will definitely never be zero. Alright? So, when you vectorially add them up, you will never get a zero. For you to get zero, they must point in opposite directions. Okay? Hope this helps. I'll see you again in the next lesson.